We have here another example where we're going to be looking at drag. So we have a car, the profile as seen from the front. So if we were looking at the car from the front, which of course this is not a best drawing, but it's telling us it's 1.6 meters wide and 1.4 meters high. The aerodynamic body shaping gives a drag coefficient of 0.35. That's the C in the drag equation. We want to know at what speed does the magnitude of the drag equal the magnitude of the rolling friction. So this is a little different in that we're not looking at the acceleration, we're not looking at whether or not the car's traveling at a constant speed. If we put this statement in equation form, we want to know when the drag force, the magnitude of it, will equal the rolling friction force. In a free body diagram, I would need to draw from the side. The drag force and the rolling friction are actually in the same direction. There would be some sort of force from the engine moving us forwards. Technically, it's keeping us going on the ground, but the engine is required to keep the tires moving. There would be a normal force up, a force of gravity down. So this problem's a little different in that they just want to know when the drag force equals the rolling friction. Our author, we're using the equation that they give us. So that approximated equation, 1/2 C rho AV squared, is going to equal, rolling friction is the coefficient of friction times the normal force. Both of these equations individually we can get off the test notes. So for friction, we do need to know what the normal force is going to be. In our free body diagram, the only forces in the y direction are the normal force and the force of gravity. Cars just driving down the road, there's no acceleration in the y direction. So it is valid to say that the normal force would equal mg in this case. So I'm going to come back and replace n with mg. So we're looking for the value of v when these are equal. If I pull the 2 over, I end up dividing by C, rho, and A, and then square root. So mu, the rolling coefficient of friction, is the 0.02. M is the mass of the car, the 1,500 kilograms. G, 9.8. C, they gave us in the problem as well. Rho, we're going to use that 1.3 kilograms per meter cubed that the author gives us in the test notes, right near the drag equation. And then A is the cross-sectional area we see if the object is moving towards us. That's why they gave us this as seen from the front. The area would be the 1.4 times by the 1.6. So they give us these values. So plugging in 0.02 for the coefficient of rolling friction, the 1,500 for the mass, 9.8, C rho, and then 1.4 times 1.6. 24. The units will be meters per second. We can work that out if we want. The mass is kilograms. The mu does not have units. The 9.8 is meters per second squared. The C does not have units, but rho has units of kilograms per meter cubed. And then meters times meters. So these two meters cancel out with two of those. The kilograms cancel. This meter comes to the top, so we have meters squared per second squared, but we will be taking the square root, and so we end up with meters per second as our answer.